The wave power group had always planned to test a string of duck models in a realistic ocean wave tank. By 1977, we knew that we would have to build it ourselves, as no suitable tank existed anywhere. From the earliest days, Stephen Salter had started to develop a completely new kind of wavemaker. We lined one side of our new tank with our latest version of these absorbing wavemakers. This tank, with its ease of control and its rare and unusual waves, was to become the first of a new generation of wave tanks around the world. Here we request a single regular wave from the tank control processor. At the beginning of a model test program, three-dimensional waves can be too complex, and you may need to spend time working with such waves of constant length and height. The yellow fabric rolling seal along the front of the wavemakers keeps the paddles in the dry and avoids awkward resonance effects from their back surfaces. We used wire drives and second-hand servo motors. There's a tacho generator on the other side of the motor and a piezoelectric force sensor under the wavemaker pulley. By adding a delay or phase difference to the signal between each wavemaker, we can make the waves swing around to some other angle. This wavefront is defined by a constant height, period and angle. To build up more complex sea states, we would add more wavefronts. Two wavefronts of opposite angles combine to make the most basic three-dimensional pattern, an unnaturally symmetrical sea state. In those days, our wave-making processor had to do its maths in real time. It could just manage a maximum of 70 wavefronts. Nowadays we can have as many as we want, so by blending together those 70 distinct heights, wavelengths and angles, we could get very realistic sea states. This was a 1-second Pearson-Moscovich spectrum with Mitsuyasu spreading function, standard stuff that oceanographers would recognise. Like the throw of a dice, real ocean waves are random. You don't know exactly what's going to happen next. We preferred pseudo-random, fixed-length wave patterns that would repeat exactly, again and again. Look at photos A and B. The ducks are in different places, so they weren't taken at the same time, but see how the wave patterns come together. We know the past and the future of these sea states. We could get strange waves that had never been seen in nature. The first of these that we discovered we called the Bullseye. The wavefronts all had the same period, but their angles and phasing were calculated to bring the troughs and crests together at a chosen place. This is a deep water plunging breaker, a wave of unusual steepness. Water waves are dispersive, which means that long waves travel faster than short waves. In a realistic sea spectrum, we can arrange for the different component wavefronts to catch up with each other at some precisely defined place and time in the future. This trick was popular with television producers making programs about foul weather. See how localized the extreme wave event was. Another vessel in another place survived. The hardware and software that we designed for our wide tank has lately been much further developed by our colleagues Matthew Ree and Doug Rogers at Edinburgh Designs. They've won a global market for precision wavemaking and tank design. These example jobs in Korea, the Philippines, France and the United States range from national research facilities to theme parks. Thanks to Edinburgh Designs, the force-based absorbing wavemaker, which we developed long ago as a tool for wave power research, has finally become an export earner.